Welcome to Unit 1, Lesson 1, the first lesson of the course. You'll notice here in all of these recordings you're going to have in the upper left corner the shorthand for what unit and lesson you're in, and then I will have the objectives for the course listed, and you got to just hear my cell phone making a little text message sound there. Maybe you did, maybe you didn't, I don't know. But so I'll have the objectives listed at the start of each lesson, and then you'll also find as you go through these that the homework assignments are directly correlated to these recorded videos. So everything I cover here in Unit 1, Lesson 1 is the stuff you're going to find on the Unit 1, Lesson 1 assignment. So you'll probably do yourself a favor if you go straight from this video to working the homework. So without further ado, let's get started. We've got three objectives. First, we're going to identify the greatest common factor from a list of terms. We're also going to write a polynomial in factored form, and we will factor polynomials by grouping. All right, let's start. GCF, greatest common factor. What does it mean? Well, it kind of defines itself, but I think the best way to see what it means is by just looking at an example. So let's take a simple example with a set of three numbers. Let's say you have 12, 21, and 36. And I want to determine what is the greatest common factor of these three numbers. Well, what do I mean by that? Well, greatest, largest, right? Common, what do they have in common? And what is a factor? Think, what are factors in general? Factors are numbers that multiply to make another number, or another way to think of it is they divide into a number evenly. So, for instance, if I take 10, the number 10, what are the factors of 10? Well, you've got 1 times 10 can make 10, and 2 times 5 can make 10. So the factors of 10 would be all four of those numbers, 1, 2, 5, and 10. All of these are factors of 10. So that's what we mean when we talk about a factor, a number that divides into another number. So if we want the greatest common factor, what we want is the largest number that will divide into all three of these. You may be able to do this one just by looking at it, because these numbers are small enough in this example that you can probably just test and check until you find the right answer. But there's also a systematic approach that will help you out when you get into numbers that are a little bit more complicated. So let me erase this, what I just put over here on the side. I need that space. And let me come over here, and we're going to do a factor tree. You've probably seen a factor tree before, but I'm going to do one for each of these three numbers. So I'm going to break down 12 into some factors. There's more than one right way to do this. Right? I could say 12 is 2 times 6, or I could say it's 3 times 4. Either way, you're going to end up with the same answer. But I'll go with 2 times 6. Now what do I do? Well, 2 is a prime number. Anytime I get to a prime number, I'm going to circle it because I know I'm done. That's the point of this. We're going to break it down into a list of prime factors. And 6, I can keep going because 6 breaks down further into 2 times 3. So now what I'm saying here is, what is the prime factorization? That's what we just did. We did the prime factorization of 12 is 2 times 2 times 3. I'll just write that a little smaller underneath the 12 over here. 12 is 2 times 2 times 3. All right, let's do the same thing for 21. 21's pretty quick. 21, one step. The only thing you can do is 7 times 3, or 3 times 7. The order doesn't matter. Right? Well, those are both prime numbers, so we're done. There's not any further that I can break that down. So 21 is just 3 times 7. Now let's do 36. I may need a little bit more space for this. I'll squeeze it over here underneath. 36, again, like 12, there's a lot of ways you could go here. You could go 6 times 6, 12 times 3, 9 times 4. Any of those work. You'll get there eventually. I'm going to go 9 times 4, just because it keeps things even. You'll see in a minute. 9 and 4, now those are factors of 36, but they are not prime factors because they're not prime numbers. Okay, so I need to keep going because both of them will break down. 9 breaks down into 3 times 3, 4 breaks down into 2 times 2, and now I'm done. These are all prime numbers here. So then my prime factorization of 36 is 2 times 2 times 3 times 3. Okay, now I've listed it out this way on purpose so we can compare. Well, if we want the greatest common factor from this list, then first of all we need to find anything in common. So let's go and see what do they have in common. The easiest one to start with is 21. Look at the list for 21 because it's only got two numbers in it, a 3 and a 7. Well, the other two factorizations do not have a 7, right? So the only thing that we're going to have in common is this 3. There's a single 3 there. There's a single 3 there. There are two 3's over here in 36 tree, but we can only pull out one of them because there's only one 3 that all three numbers have in common. So what does this tell me? That's the only thing they share, so that is the greatest common factor for those three numbers. For 12, 21, and 36, the greatest common factor is 3. Okay, so when you have whole numbers, you can do a prime factorization like that to compare and determine what the solution should be. What about when you have terms that look like this? X squared, 3x to the 5th, and x to the 4th. This one actually goes pretty quickly because this is easy to list out the factors really nicely. Well, think, what is x squared? If you break x squared down, we don't know what x is, that doesn't matter. What is x squared? Well, x squared is just x times x. Right? That's all it is. There's only two factors, x times x. Alright, now let's look at the middle number. We're done with the first one. We just factored it. I'm going to put commas between these factorizations to keep everything lined up. 3x to the 5th. Well, there's a 3. 3 is a prime number. I can't break it down any further. And x to the 5th, well, that means there's 5 x's. So x times x times x times x times x. And then last I have x to the 4th. So that's just x times x. Well, my x got cut off there a little bit. Let's see if we can fix that. Every now and then my fancy electronic pen here doesn't really do what I want it to do. Alright, there we go. Alright, so we have x squared, 3x to the 5th, and x to the 4th, and I've just broken them down into a list of factors. Well, you can see pretty quickly, it's going to be easy to pick out the greatest common factor. I've got 2x's here, 2x's here, 2x's here, and that's the most I can pull from all of them, right? Because that's x squared. That's all of the first term. I had 3 terms and I'm using all of the first one. So that's the most I could possibly factor out. So that real quick tells me what's my greatest common factor. In this case, my greatest common factor is x squared. X times x is x squared, right? And what we're saying is that's the largest term you could divide into all 3 of those. You can divide x squared into x squared. You can divide it, sorry, let me catch it. You can divide it into x squared. You can divide x squared into 3x to the 5th. Think about what you would get. I took 3x to the 5th and divided it by x squared. You have all of these x's. I'm going to squeeze them in there. And you've got 2 of them down here. So what happens? Well, 2 of those 5 x's on top are going to cancel out, and you're left with 3x to the 3rd, because there's 3 x's left on top. So x squared did go into it evenly, and went into it a whole number of times. And then, of course, x to the 4th divided by x squared would give me x squared also. So my greatest common factor is x squared for that list. Alright, let's move on. Let's do one that has a little bit more complexity to it. Negative 18, a cubed, b squared. Negative 63, a to the 5th, b. And 27, a to the 6th, b squared. Now, we're looking at this set of 3 terms. One thing that'll throw people off is negative numbers. Don't get thrown off by negative 18 and negative 63, because remember, the negative numbers have the exact same factors as the positive numbers. Right? A negative 18 is still divisible by the same numbers that positive 18 was. So it has the same factors. Let's not get thrown off by the negative. It really doesn't affect the problem at all. It's just there to distract you. And so really how you want to work this is you want to split it into 3 parts. You want to consider, let's take the, and there goes my cell phone buzzing at me again. I am popular today. Let's take the 18, 63, and 27, and we'll consider that as one part, the whole number part. And then we're going to take the a's. We've got a cubed, a to the 5th, a to the 6th. We're going to try to determine what's the greatest common factor among those. And then we've also got the b's, which we will consider separately. So if we take those 3 parts, take the greatest common factor of each part, then we'll smush it together and we'll have a final answer. The a's and b's are actually the easy part, so let's start with the numbers. It's just like what we did the first time. We're going to do a factor tree. So let me take my 18 here. 9 times 2, 6 times 3, whatever makes you happy. Doesn't bother me either way. We'll do 9 times 2 this time. 2 is a prime number, and 9 breaks down into 3 times 3. So there is my factorization of 18. It is 2 times 3 times 3. Let's do 63. Really? You could do 21 times 3. I doubt any of you would have thought of that right away. You probably look at 63 and you see 9 times 7. That's most likely what you see. Well, there's a 7. That's a prime number. And again, we have this 9 that breaks down into 3 times 3. Okay, last we have 27. Pretty quick. Again, instead of 9 times 2, it's 9 times 3. So again, we have a prime number here. We had a 9 in each case. What does that tell you? That's probably a factor. That's common to all of them. Interesting. 9 breaks down into 3 times 3 again. All right. So what do they all share? Well, let me use a different color to make this stand out. They all have these 2 3s, right? There's 2 3s here. There's 2 3s here. There's 2 3s here. Which, of course, we know equals 9, because they all had, if I go up a step higher, I say, well, I should not erase my 9. I didn't want to do that. I meant to circle it, not erase it. Oh, this pen, it's so fun. They all had these 9s here, which is 3 times 3. We just broke it down a little further. So what is my greatest common factor? My greatest common factor is 3 times 3, which, of course, is 9. So that's going to be in my answer. So when I come over, I'll write it over here on the right side. My GCF then is going to be 9 something. Okay, that was the whole number part. Now let's look at the A's. In this first one, I have a cubed. In the second one, I have a to the 5th. And in the last one, I have a to the 6th. So what do you think the greatest common factor is? Well, I can't pull out more than 3 a's, right? Because this first term over here only has 3 a's. It's a cubed, so that's the most I could factor out of that term. And of course I could also factor out 3 a's from the other 2. So that's pretty simple. A cubed is part of my GCF. So when it comes to the variables, all you really have to do is find the smallest power on any of the terms. So again, let's apply that logic with the b's. I've got a b squared. I've got a b to the first power. Of course, we don't write the 1 as an exponent, but it's understood. And I've got another b squared. So I can only factor out one single b from all 3 of those terms because the middle term only has a single b in it. And there we have it. Our greatest common factor is 9a cubed b. And that is the largest term we could factor out of all 3. Or another way to say it is the largest term we could divide into all 3 of those in our list. Okay, let's take this concept and apply it. We're moving into objective 2 now. Let's factor polynomials. Let's write polynomials in factored form. So let's start simple. 6t plus 18. It is a polynomial because it's got 2 terms. It's technically called a binomial. Bi meaning 2, right? Well, so we want to know what can we factor out of each term. We've just looked at a list of terms and factored and found the greatest common factor. Now we want to find the greatest common factor between 6t and 18. Of course, this one's pretty quick because it's pretty easy to tell. You don't have to go through a list to see that the greatest common factor is 6. So what can I do? I can factor that 6 out, which essentially means I'm going to divide both terms by 6, and I'm going to pull that out front. So if I factor a 6 out, we want to think, well, if I take 6t and I divide it by 6, what do I have left? The 6's cancel out, and all I have is a t. So I'm going to open parentheses, and I have a t. Then we don't want to forget our plus sign. Our plus sign is still there, right, between the terms. And then we have 18. Well, if I took 18 and divided it by 6, what do I have? I have 3. So there is the factored form of that polynomial. I took 6t plus 18. I pulled to the front the greatest factor that I could, which in this case was 6. And that left me with t plus 3. And of course you could use distributive property to verify that this is correct, right? Because we could come back in here and say, well, let's multiply this out using distributive property, and that gives me 6 times t is 6t plus 6 times 3 is 18. And I'm right back where I started. So we've verified that what we did is correct. Mathematically, we didn't do anything wrong. All right, moving on. What do I want to do next? I want to do y to the 5th minus y to the 7th. I just got done saying a minute ago that variables are easy, right? Right, of course they are. All we have to do is say, well, how many y's can I factor out of each term? I've got 5 y's on the left, I've got 7 y's on the right. So the most y's I can pull out is 5. So let's factor out y to the 5th. Well, what happens if I have y to the 5th and I factor the whole thing out? Well, essentially what I'm doing is I'm dividing it by itself. And what is anything divided by itself? It is 1. I factored all of it out, so there's a 1 there, not a 0. Some people mistakenly assume that must be a 0, but that would not work out if you tried to distribute it back out. That term would be gone. We need a 1 to stay there. Minus, now we had y to the 7th. We factored out y to the 5th, so how many y's are left? Well, we removed 5 of the 7 y's, so there's only 2 remaining. And if you remember your rules of exponents for multiplication and division, then you can verify that that is correct by doing the distributive property. But there it is, factored form. All right, one more of these and then we'll move on. This one will look slightly more complex. Let's take 3/7. Okay, it'll look a lot more complex. P squared q to the 4th plus 1/7 p cubed q to the 5th minus 5/7 p cubed q cubed. All right. Everyone loves p's and q's. Everyone loves fractions. I don't know, everyone hates fractions, but that's okay. Don't get distracted by the fractions. That's why we're doing this. We still can think, what's the greatest common factor between 3/7, 1/7, and 5/7? Now, I bet if they weren't fractions, you'd know right away. If you said, forget the sevenths, forget the denominator, and just say, what's the greatest common factor between 3, 1, and 5? Well, they don't share any factors, right? 3, 1, and 5, they don't share anything. So the only thing you could pull out is a 1, which doesn't seem helpful. But now think about it as a fraction again. 3/7, 1/7, 5/7. What's the greatest common factor there? 1/7 is. I can factor out 1/7, so I'm going to do it. I'm going to factor out 1/7. Now let's look at our p's and q's. Let me use my highlighter here to point this out. Look at our exponents on the p's. I've got a 2, a 3, and a 3. So how many p's can I factor out? I can factor out 2 of them. I'll factor out p squared. And now for the q's, I've got a 4, a 5, and a 3. So how many q's can I factor out? I can factor out 3. Most I can pull out. Now we open our parentheses and we have to look at what's left in each term. Alright, so if we take, let me write this over here to the side in a different color. If we took 3/7 p squared q to the 4th, that was the first term, and we divided it by 1/7 p squared q to the third, right? Because that's what we're doing here. That's what we're factoring out. Well, what do we have left? The p's are easy, right? The p's cancel each other out. They're gone. How about the q's? Well, I got 4 q's on top. I got 3 on the bottom. So this 3 is going to cancel out all but one of these 4 q's. So all I'm going to be left with on top is just a single q. Now the fraction part. What is 3/7 divided by 1/7? Well, it's 3. The 7's cancel each other out. You've got 3 over 1 remaining. Okay? 1/7 times 3 is 3/7. That should make sense. So my answer here is 3q. That's all that's remaining of the first term. I factored out the 1/7, I factored out both p's, and I factored out 3 of the 4 q's. Alright, then we have plus. Now the middle term, it just had a 1/7 for a coefficient, so that coefficient is gone completely. We factored out 2 p's. There were 3 p's, so there's a single p remaining. There were 5 q's, and we factored out 3 of them, so there's q squared remaining, because we removed 3 of the 5 q's. And then in the last term, we have a minus sign. We have 5/7. We factored out 1/7, so what's remaining is 5. We had p to the third, so all that's left is a single p, because we factored 2 of them out. We had q to the third. Well, we factored out all 3 of those q's, so there's no q's remaining, and we're done. There is the factored form of that polynomial. Oh yes, and you are excited about factoring polynomials at this point. I know you are. I appreciate your excitement. Alright, let's move on to the last objective of this first video. And by the way, all the videos won't necessarily be the same length. This one is kind of long, but they should all be somewhere between 15 and 35 minutes. 15's on the short end. They'll probably average around 25 minutes or so. But that's not too much. Not too much at once. Hopefully that's a digestible chunk for you. Alright, our last objective is to factor a polynomial by grouping. And this occurs when we have 4 terms and it doesn't immediately appear that there's anything common to factor out of all 4. But first, let me do something, show you something else first, because people get confused when there's parentheses involved. Let's say we have 5 times x plus 3 plus y times x plus 3. Let's say we had something that looked like that. Well, keep in mind what's going on here. We have 2 terms here. We have one term, 5 times x plus 3, and another term, y times x plus 3. Each of those terms has 2 factors. One factor is this 5, and another factor is x plus 3. Now you're thinking, well, x plus 3, but there's a plus sign there. That looks like more than one thing, more than one factor. But keep in mind, it's in parentheses. Because it's in parentheses, and that whole thing, whatever x plus 3 is, it's a single chunk. Whatever that number is, it's being multiplied by 5. So we've really only got 2 things being multiplied here, 5 and x plus 3. So x plus 3 is a factor by itself. And then you've got the same dynamic going on in the other term. You've got y as a factor, and x plus 3 is a factor. Okay, so what's the point? Well, the point is, x plus 3 is a common factor. Both terms have a common factor of x plus 3. So I can factor the x plus 3 out. So if I pull x plus 3 to the front, and I say open parentheses, well, now let's look back at the original problem. What's left? I took this first term, I factored that x plus 3 out, all that's remaining is 5. Then there's a plus sign. I took the second term, I factored that x plus 3 out, all that's remaining is a y. Okay, so this concept that we can factor out a term, a factor that is in parentheses that may not look like it's a single factor, but it is, that's important, because that helps us accomplish factor by grouping. Alright, here we go. Let's look at an example that's not already set up in that format. xy plus 2x plus 3y plus 6. Alright, This is where the factor by grouping comes in. As you look at this, you see 4 terms, and there's not a single common factor that I can pull out of all 4 terms. But if I come in here and group them, and I say, well, let's put parentheses around these first 2, and then let's put parentheses around these last 2, and let's just consider them in these groups of 2, now I can factor. Because now, as you look at the first 2, what do they have in common? Well, there's xy and 2x. So what they have in common is an x. I can factor out that x. And what's left? Y plus 2. Because I factored the x out of both terms. Now, as you look at the second pair, we've got 3y plus 6. What can I factor out of 3y and 6? I can pull a 3 out. And what am I left with? Y plus 2. And now notice this looks very similar to the problem right above it at this point, because now we have this y plus 2 showing up in both terms. So I can factor the y plus 2 out, and that gives me y plus 2 times what's left in the first term. All that's remaining is an x, and all that's remaining in the second term is a 3. So there's my final answer. I factored by grouping. I took a 4-term polynomial and factored it into 2 terms being multiplied, which actually is very beneficial. As we get further along, you'll find out why. And if you want to check that, you can always FOIL it back out. Those of you who remember how to multiply 2 binomials, you can always multiply that back out and check and see that you do get what we started with. Okay, let me see. Let me find a winner here. Let me find another good example that will. All right, here we'll do one more and then I'll be done. 15x cubed minus 10x squared plus 6x minus 4. All right, again, as we look at this, let's see, is there anything we can factor out of everything? As you look at the last term, it's a 4. It doesn't have any x's on it. So the only thing you could pull out is a 4 or a 2 maybe, and 15 is not divisible by 2, so we can't do that. So this is a factor by grouping situation. So I'm going to come in here and put some parentheses around this and group it. Alright, let's look at this first pair. 15x cubed, 10x squared. Well, 15 and 10 are both divisible by 5, so I can factor a 5 out. And then I've got x cubed and x squared, so I can factor x squared out. And what does that leave me with? It leaves me with 3x, right? Because 15 divided by 5 is 3, and x cubed divided by x squared is x, minus, what's 10x squared divided by 5x squared? Well, the x squareds cancel out, and all that's left is 2. 10 divided by 5. And then looking at the second pair, 6x minus 4. All I could factor out there is a 2. So I've got my plus sign still, and there's a 2. Well, if I take 6x and divide it by 2, it becomes 3x. If I take 4 and divide it by 2, it becomes 2. And the minus sign stays. We didn't change it. So notice, again, we have a common factor. We have 3x minus 2 showing up in both terms. So we go to our last step. We factor the 3x minus 2, bring it to the front. And what does that leave me with? I have 5x squared plus 2. Because when I pull that 3x minus 2 out of this first term, all that's left is 5x squared. And when I pull it out of the second term, all that's left is 2. Okie dokie then. That is it. You should be prepared thoroughly to do the Unit 1 Lesson 1 assignment.